Hello friends, welcome to our YouTube channel, Gajpal A Learning. In this video we are going to study about the topic, Werner's coordination number, titration curve of complexometric titration, and stability constant or formation constant. So let's start the video. Werner's coordination number. Werner's coordination number, also known as the coordination sphere, refers to the number of bonds formed between a central metal ion and its surrounding ligands in a coordination complex. Alfred Werner, a Swiss chemist, developed the concept of coordination numbers in the early 20th century, and his work laid the foundation for modern coordination chemistry. The coordination number is an essential factor in understanding the geometry and properties of coordination complexes. It helps describe the spatial arrangement of ligands around the central metal ion and has a significant influence on the complex's stability and reactivity. Common coordination numbers include: first, coordination number 2, linear. In this arrangement, two ligands bond to the central metal ion in a linear fashion, forming a straight line with an angle of 180 degrees between them. An example is AgNH3, 2+ ion. Second, coordination number 4, tetrahedral or square planar. In this case, the central metal ion can be bonded to 4 ligands, resulting in either a tetrahedral or square planar geometry. Examples include NiCl4, 2, tetrahedral, and PtNH3, 2Cl2, square planar. Third, coordination number 6, octahedral. The central metal ion forms bonds with 6 ligands, leading to an octahedral geometry with bond angles of approximately 90 degrees between adjacent ligands. Common examples include Cr, H2O, 6, 3+, and CO, NH3, 6, 3+. Fourth, coordination number 8, cubic. In rare cases, a central metal ion can be bonded to 8 ligands, resulting in a cubic geometry. An example is MOCN8, 4. Note: the coordination number is a fundamental characteristic of coordination complexes and is determined by factors such as the size and charge of the central metal ion and the nature of the ligands. Different coordination numbers can lead to distinct geometries, which, in turn, influence the complex's stability and reactivity. Understanding coordination numbers is crucial in predicting the behavior of coordination compounds in various chemical reactions. Next, titration curve of complexometric titration. The titration curve for complexometric titration is a graphical representation of the change in a property of the solution, usually pH or potential, as a function of the volume of the titrant, chelating agent, added. Complexometric titration is commonly used to determine the concentration of metal ions in a sample. Here's a detailed explanation of a typical titration curve for complexometric titration. First, initial region. At the beginning of the titration, before adding any titrant, the solution contains a known volume of the sample containing the metal ions. The pH of the solution is typically measured or monitored continuously throughout the titration. In the initial region of the titration curve, the pH remains relatively constant and corresponds to the pH of the original sample. Second, titrant addition. As you start adding the chelating agent, titrant, it begins to react with the metal ions in the sample. The chelating agent forms complexes with the metal ions, gradually reducing the concentration of free metal ions in the solution. As a result, the pH of the solution begins to change, typically increasing, since many common chelating agents are bases. 3. Rising portion of the curve. This part of the curve shows the pH increasing gradually as more titrant is added. The pH change is more pronounced as the concentration of free metal ions decreases. The slope of this rising portion depends on factors like the stability constant of the metal chelate complex and the pKa of the chelating agent. Fourth, buffer region. In some cases, you might observe a buffer region on the curve, especially if the chelating agent is weakly basic or acidic. This region indicates the presence of a buffer system formed by the partially reacted chelating agent and its conjugate acid or base. The buffer region can cause a gradual change in pH instead of a sharp increase. Fifth, equivalence point. The equivalence point is the most critical part of the titration curve. It marks the point at which all the metal ions in the sample have reacted with the chelating agent. At the equivalence point, the pH may undergo a sudden and noticeable change due to the complete formation of metal chelate complexes. The volume of titrant added at the equivalence point is used to calculate the concentration of metal ions in the sample. 6th. Post-equivalence region. After the equivalence point, any excess titrant continues to react with the chelating agent, but the pH change becomes less dramatic. In this region, the pH may continue to increase slightly or level off, depending on the specific reaction. 7th. Endpoint. The endpoint of the titration is the point at which the pH change is practically detected through an indicator, pH meter, or other suitable method. It may not necessarily coincide exactly with the equivalence point but is used as a practical indicator for the end of the titration. Analyzing the titration curve allows precise determination of the metal ion concentration in the sample. The specific shape of the curve depends on factors like the choice of chelating agent, metal ion, and the presence of interfering substances. Indicators or pH meters are commonly used to identify the endpoint, and stoichiometric calculations are performed using the volume of titrant at the equivalence point to determine the metal ion concentration accurately. Next is stability constant or formation constant. A stability constant, often denoted as K-stab or Kf, formation constant, is a fundamental concept in chemistry, especially in the context of complexation chemistry and equilibrium reactions involving complex ions. It quantifies the degree of stability or strength of a complex formed when ligands, molecules or ions coordinate with a central metal ion to create a complex ion. Here's a detailed explanation of stability constants. First, formation of complex ions. In chemistry, many metal ions can form complex ions when they react with ligands. These complex ions consist of a central metal ion, often referred to as the metal center, surrounded by one or more ligands. The formation of these complex ions is governed by equilibrium reactions, where the forward reaction involves the coordination of ligands with the metal ion, and the reverse reaction involves the dissociation of the complex. Second, equilibrium constant K. Just like any chemical reaction, the formation of a complex ion has an associated equilibrium constant K. For the general reaction, m power n plus plus xl rightwards harpoon over leftwards harpoon, mlx power n plus. M power n plus represents the metal ion. L represents the ligands. mlx power n plus represents the formed complex ion. The equilibrium constant K for this reaction is given by K equals mlx power n plus divided by m power n plus into L power x. mlx power n plus is the concentration of the complex ion. M power n plus is the concentration of the free metal ion. L poser x is the concentration of the ligands raised to the power of their coefficient in the reaction. Third, stability constant K-stab or Kf. The stability constant K-stab or Kf is a special type of equilibrium constant that specifically applies to complex formation reactions. It represents the equilibrium constant for the formation of the complex ion, and it quantifies the degree of stability or strength of that complex. Mathematically, it is defined as K-stab equals 1 per K. Higher values of K-stab indicate more stable complexes because a large K-stab means that the complex formation is favored over the reverse reaction, dissociation. Fourth, units of stability constants. Stability constants are dimensionless because they represent a ratio of equilibrium concentrations. Fifth, importance. Stability constants are crucial in coordination chemistry, as they help chemists predict the behavior of metal ions in solution. They aid in understanding which ligands are most effective at forming stable complexes with specific metal ions. They are used in various fields, including analytical chemistry, environmental chemistry, and biochemistry, to study the behavior of metal ions in complex biological systems. Sixth, examples. An example of a stability constant is the formation constant, Kf, for the complex ion, Cu, NH3, 4(2+) in the reaction. Cu2+, plus 4 NH3 rightwards harpoon over leftwards harpoon, Cu, NH3, 4(2+). The higher the Kf value for this reaction, the more stable the Cu, NH3, 4(2+) complex is. In summary, stability constants are fundamental in quantifying the strength and stability of complex ions formed when metal ions coordinate with ligands. They play a crucial role in predicting the behavior of these complexes in various chemical and biological systems. Thanks for watching this video.